All right. Well, as always, I do appreciate the opportunity to present some material here for the CR guest speaker series. Now, despite a relatively quiet tornado season for really most of the Central Plains last spring, as usual, you get into late May, it'll give you at least a couple events to review, and that includes this Benkelman, Nebraska Tornadic supercell, which is over Goodland CWA. So, and I'm not picking on Goodland, just happens to be a decent case, neighboring FO. The one thing I will admit, I did not interpret what was ongoing in real time correctly with this, and that's coming from somebody like John that's been looking at a lot of stuff for a while. And so, after doing a little bit of investigation and analysis, it's kind of why I'm here to illustrate this, and overall show the key findings from this case that hopes to improve warning decision making, not just for myself but for others. And so, for those that watched my High Plains conference talk, on this case, I think I just muted myself. Am I back?
Yeah, you're back.
So. Okay. Anyway, for those that watched the High Plains conference talk in this case, I don't know what I'm doing. I keep muting myself. Well, anyway, I'll try this, try to advance the slide here. So for the third time, for those that watch my High Plains conference talk, fear not. If I can get it to advance, hold on here. I don't know what I'm doing. There we go. Okay. Fear not, even though it's Groundhog Day, I'm not Ned Ryerson asking you to add life insurance. So that's my cheesy slide for the day. I did have to add that, sorry. Just what it is. Okay, so just as a quick review of what happened on this day, just to gain some background information. The Benkelman storm was, part of a fairly typical late May, essentially mini outbreak of tornadic supercells along a slow-moving warm front. You can see here extending from Nebraska Panhandle roughly into central Kansas. So, basically by itself, nothing really out of the norm with this storm. For that matter, really, the overall event. This stuff happens all the time in late May across the Central High Plains. So again, nothing really earth-shattering in that aspect. So in terms of the Benkelman event, there was a string of tornado reports starting a few miles north of town, beginning at roughly 3:25 p.m., which, as you can see here, the Goodland office categorized as Tornado 1. And so this continued roughly northward along, I believe it's State Highway 61 for another 8 miles as a second tornado, and actually a satellite vortex, Tornado 3, developed before dissipating. Of course, tons of chaser picks emanating from the storm, which I have taken the liberty of using a few today. And I'll just add this, while not officially documented, some chaser reports and video also illustrate a possible fourth tornado near what is the Dundee-Hitchcock County line. So not officially documented, but lots of chaser pics and videos on that. So since it's fairly obvious from the title that I'm going to delve into ZDR arcs and buoyancy related issues, I thought it'd be good to quickly review why we look at this stuff via some of the former TWIP, now CWIP modules. And one of the key reasons for assessing the existence of an arc along what would be the forward flank reflectivity gradient region is that it helps anticipate low-level mesocyclone intensity trends. And specifically, the ZDR arc is really just a manifestation of hydrometeor size sorting, primarily caused by the mean low-level storm relative wind. So subsequently, it gives us kind of a mechanism to qualitatively assess the amount of streamwise vorticity feeding into the low-level meso. You can see I've kind of got a crude photograph over here. And so that's important, though, because it provides a prognostic capability with low-level meso strength rather than diagnostic rotation values. Less reactionary in that case. We're able to anticipate. So it is important to note that the simple existence of an arc in, say, higher low-level SRH environments, for example, 0 to 1 SRH, say over 200, is typically sufficient evidence that the storm scale is nudging that background SRH to intensify or maintain the low-level mesocyclone. And so that works pretty well with one important caveat. And that occurs in more weak to moderate low-level shear environments where the storm has to do more than just essentially nudge the background SRH, but rather through storm scale processes, it has to provide kind of most of the necessary streamwise vorticity for the local meso. And so fortunately, we can account for this by using what's called the KDP foot and ZDR Arc Separation Vector in comparison to storm motion. Now we do this in order to determine really the angle between the two vectors, and specifically that's important because the larger the values, it qualitatively infers a higher storm scale SRH. Now, just a brief toss in here, but there is active research, and specifically this is some information from Matthew Wilson at UNL, to begin kind of automating this calculation. As you can see with, in this case, not only the outlines of the ZDR Arc in blue, but the KDP foot in green. And we also have a calculation of the separation vector angle, which kind of hard to see in the text there in the lower right panel, but it's only just a hair under 10 degrees, which is obviously not very good. So, and in a lower SRH environment, which is what this storm existed in, that really isn't going to be much to really hang your hat on in terms of intensifying the low-level meso. Now, to be blunt, this type of information being fed into machine learning is going to be really difficult to beat, especially if a forecaster still kind of hangs on to legacy rotation VROD analysis. However, as I'll detail in this case, there are some limitations with automated ZDR Arc detection that will incorrectly assign, let's say, a low genesis probability or low mesocyclone intensification when things are actually much different. So, this is where we can still defeat the machines if we choose to understand. That's why understanding the conceptual models, understanding the weaknesses and strengths of algorithms is very important. So in particular, this connects back to a TWIP module we provided, it's been a few years ago, but involving how by using dual pole, one can infer the degree of essentially storm scale negative buoyancy that may inhibit tornadogenesis. And that's done through these ZDR Arc disruptions. And so this is based on a couple decades of research, not my own ideas, but showing essentially how we can infer hydrometeor character from dual pole products and especially associated buoyancy profiles. So in essence, the idea here is that a region of reduced CC and around ZDR can kind of tell us about the hydrometeor character, but also inferring buoyancy and specifically how it has kind of these reverberating effects on things that ultimately inhibit tornadogenesis, as seen in the various bullet points here. So this takes us back to ZDR Arcs and what you can really infer when the ZDR Arc is disrupted or completely disappears. So as illustrated in this conceptual model, the ZDR Arc shown in the red shaded area there becomes disrupted due to this region of low ZDR, which is seen in the blue shaded area. And really the key takeaway from this conceptual model is that it suggests that a region with a strong rain hail mix and or wet melting hail is introducing very negatively buoyant parcels into that near surface airstream that John talked about that feeds the region under the low-level meso. So just to tie back into John's talk on the LFEE, this airstream in tornado events, we need to see making that cyclonic turn near the low-level meso for anticipating tornadogenesis. And that's where we got to hope there's not too much of a momentum surge associated with negative buoyancy that would cause it to blow past. So that's why in arc disruption cases with tons of wet melting hail, in theory, we would see more of the conceptual model on the left here, since there's this infusion of more negatively buoyant air and momentum into the LFEE that ultimately causes, at least in this concept, the airstream to surge beyond the low-level meso with tornadogenesis failing. So, and here's just a quick example of what that might look like. You can see we have both a disrupted arc and associated band of more or less negative or near zero ZDR along with reduced CC cutting across the rear flank, forward flank interface. Now the LFEE airstream, you can kind of see here is emanating from deeper into the storm core. Initially it's kind of there's that, zero isodop or a velocity minimum with outbound. And again, we're looking at the upper right panel. And it's basically very deep in the core and then ultimately starts surging well past the location of strongest lift near the low-level meso. And that's shown by the stronger now inbound values. And that's the 88D is off to the southeast in this case, but the stronger inbound values extending beyond even the hook. So as a reminder, John briefly mentioned this, but I'm going to do a shameless plug here. Many of these key takeaways from the TWIP and CWIP training modules on Supercell-based Tornadogenesis is available in the recently updated kind of radar feature reference guide. And this includes, of course, specific features illustrated in the leftmost column, with then various things here such as associated primary application, skill to anticipate genesis, and of course, important notes included here along with subsequent pages, which I'm not going to show you, showing examples of these features. So just a good thing to reference, especially as we get out of the Arctic air that we're currently dealing with. So that's kind of it for the basic review. Put that behind us. So we go back to the Benkelman event. Well, obviously, we've had a tornado, yet we also had a ZDR Arc disruption. So what's going on here? Before we go too far, I just want to make sure that, as mentioned in the CWIP, TWIP, ZDR Arc modules, it is good to remember that whenever freezing levels are fairly low in altitude, that you can get resultant non-uniform beam filling that can more or less mask the ZDR values to where it appears you have a disruption or maybe don't even have an arc, when in reality, the full ZDR exists, it's just at a level below the 88 Deacon sample. And so just a reality check there. And further, we obviously haven't solved the horizon issue. So hence, even if the freezing level is above, say, 3 kilometers AGL, assessing storms at ranges of, say, 80 to 90 nautical miles is, first of all, it's not giving you any details of the features in the low levels where a ZDR Arc exists. Plus, you may start dealing with non-uniform beam filling at this range. So now with that stated, this case we're looking at here is late May in the Central Plains, freezing levels over 3 kilometers AGL, and the Goodland 88D half-degree slice is sampling just a little over 1 kilometer AGL. So really, in this case, non-uniform beam filling and issues with the half-degree tilt centerline beam height, not really a problem here. So something else is going on. So let's look at the data. This is leading up to tornadogenesis to see what happened. Now in this panel and subsequent displays, I'm going to illustrate the half-degree reflectivity in the upper left, the ZDR in the lower left, KDP will be in the lower right, and then finally I'll have CC in the upper right, which I will occasionally toggle that upper right panel over to storm relative velocity. So we're going to start about 13 minutes before tornado onset. That's the first one, tornado 1, with the storm moving primarily to the north. The cells are around 45 nautical miles from the RDA, and again, half-degree beam center height. It's a little over 4,000 feet AGL. So basically, we don't see the LFVE because we're just radar beams are shooting too high at this point. But we can still indirectly infer the buoyancy nature of the parcels, feeding it by watching for these arc disruptions. And so immediately we see what appears to be a ZDR Arc on the forward flank reflectivity gradient region, which I've got outlined as black here on both the ZDR and reflectivity. I've got it as yellow in the CC just because it shows a little better there. And there's also a region of enhanced KDP north of the arc, which is the white area. Nonetheless, we have an interesting separation vector angle over 180 degrees, but since this was a day with a very elongated hodograph, that isn't necessarily a bad thing, as it still implies a fairly large amount of storm scale SRH being ingested into the mesocyclone. So toggling over to the half-degree, storm relative velocity reveals a broad but diffuse area of circulation connected to the local meso, but really nothing to write home about. However, given favorable environment and good separation vector angle, it is likely the meso will intensify. And so the key takeaway here is that given the level of meso intensification likely forthcoming and really no signs of arc disruption, this would be where a TOR warning is appropriate if one wasn't already out. So we're definitely within that range where we're meeting kind of Gipper goal lead times of T-minus 13 minutes. So we're going to skip ahead here. Not much really changes between 13 and 7 minutes, but it starts to get a little more interesting from here forward. So at this T-minus 7 minutes, we continue to find both the arc and foot prevalent with really little sign of any disruption creating buoyancy problems. Again, the separation vector angle also remains high with continued low-level mesointensification likely. So skip over here to the velocity, and sure enough, we can see in the half-degree storm level velocity, we see this upward trend in the low-level meso strength, although as predicted by the separation vector angle 6 minutes earlier. So just right there, you can start to see the prognostic capability of the arc or separation vector versus just more diagnostic rotation values. Moving ahead another minute, we see the ZDR becoming a little more narrower along that forward flank reflectivity gradient, but otherwise still really no sign of a disruption in a high separation vector angle. Further, our circulation continues to organize and strengthen. So really at this point, I thought I had a pretty good vibe on this storm and expected a tornado within a few minutes of this time period, which ultimately did happen. Not that I'm patting myself on the back, but from here forward, I'll illustrate what I missed and how really I started to veer off the path in the wrong direction. And so I'm going to go back to looking at CC in the upper right at this same time step. Not that CC is critical here, but big picture, I just wanted to include the three main dual pole products. Now, as I said earlier, everything looks good with no disruption occurring despite an narrowing of the arc. So what I didn't recognize in real time is the reason the arc was narrowing. And specifically, I've got outlined in this kind of bluish cyan color, this outline starting in the KDP, but copied into the other panels, that primarily exists between the arc and the KDP foot. And this region is dominated by, you can see, fairly low, so around 0 to even negative KDP values, with even some missing bins of KDP, but in relatively high reflectivity. So right there, you should be saying, well, what is this? You know, what might have near 0 ZDR, reduced, although not necessarily extremely low CC, around 0 to negative KDP, and then high reflectivity values. And so the answer is forthcoming. So now just 2 minutes later, we can see the arc has been completely eliminated. I mean, there's a slight hint maybe closer to the town of Max, but nothing to write home about. And so, you know, in real time, I thought, well, this is maybe a sign it's game over here with this disruption. Is, you know, signs pointing towards existence of what I thought was wet hail mixed with rain, with near 0 ZDR and reduced CC. And so introduction to significant negative buoyancy, it's going to surge past, nothing's going to happen. And of course, while I couldn't calculate a separation vector angle given the complete absence of an arc, I didn't think it really mattered, since you know, that meso would be undercut anyway. And so that obviously was a mistake, just by the fact there was a tornado. And so that blue outline, you know, of negative or 0 to negative, some even missing KDP was a clue here that now I understand, but at the time I did not. Of course, low-level meso remains decent, but again, I didn't think it mattered with the circulation being undercut with significantly buoyant air. All right, so 2 minutes later, we're getting pretty close here to where, for all intents and purposes, we're within the span where tornadogenesis is imminent. But the same signals persist, no arc, but this persistent region of around 0 to negative, even some missing KDP with an area of 50 plus dBz reflectivity. You know, low-level meso strength really hasn't changed much in the last 5 minutes. If anything, it maybe even weakened a little bit. It is important to note here that, you know, as a separation vector algorithm wouldn't provide you any useful information because there's nothing for it to calculate. And so that's why, you know, if you're just relying on the algorithms and not actually diagnosing and understanding where there's weaknesses, could potentially mislead one into thinking something that's not actually happening. And that's not a knock on the algorithm. It's just, this is where, you know, we look for, quote, targets of opportunity, and this is one of them. So at tornado time, same signals exist that could be interpreted again to mean decreased risk of a tornado, but, you know, obviously that doesn't mean anything since it was ongoing. And the low-level meso ironically shows a slight weakening, which I will say I've seen that several times, where if you're looking for this consistent signal and upward trend of low-level meso values, you're not going to see that a lot. You may in some cases, in other cases, you may see just absolutely flat line, or you may even see a decrease. So kind of, again, a reminder of what's truly prognostic versus rotation is more diagnostic. So obviously I missed something critical here. At least in real time, I was confused what was going on and questioning what I was doing, and so obviously dug a little deeper here to figure out what's going on. So take you down a little trip in memory lane here with some dual pole training courtesy of our friends from WDTD by essentially outlining values of CC, ZDR, and KDP on the associated reference charts. So first was CC. Tends to illustrate exactly what we'd figure. Its values under 0.95, but not necessarily extremely low, suggests introduction of hail. ZDR would also strongly suggest existence of hail. And now we can make the jump here that this means we have a rain-hail mix, but when we look at KDP, there's a strong sign we have little to no liquid water existing with this hail. And so why is that important? So first check, do the values in that forward flank reflectivity gradient region within T-6 fit the severe hail mixed with rain? So for reflectivity, yeah, it's in the range of that. Not likely with ZDR, possibly with CC, but definitely not KDP. We're not seeing values over 0.5. So we can immediately kind of eliminate that option, which subsequently raises questions about, is there really disruptive negative buoyancy despite the arc going away? I'll just add this. You might ask, well, how could there be negative ZDR values with hails? I thought it's supposed to be near zero as the hail tumbles. Well, just remember, not all hail tumbles. As more elongated hail can actually take on a horizontal vertical fall ascent orientation. So with me scattering, you could actually flip the sign to a negative or positive sign when you would expect the exact opposite. So just wanted to toss that in. Now we go the other direction with subsevere but dry hail. And the reflectivity is a little low, but it's not too far off. ZDR is in the range. CC looks a little high, but boy, KDP looks pretty solid. So essentially, we seem to be getting hints now that we are looking at dry hail, but not necessarily all small hail. So another way to look at this is to determine the extent of melting via a water torus around the hailstone. And that creates typically higher and higher positive both KDP and ZDR values. Now, obviously, in this case, we can't even get past step one. So we're getting more evidence we're dealing with primarily dry hail that is lower in concentration, but possibly mixed in size. So when we put this together, the middle column looks very unrealistic. In contrast, the first and third columns fit this scenario to varying degrees, as we see evidence of both, but really little evidence of wet and or hail mixed with rain. And so this becomes a critical clue here, as research such as a study from 2008 has shown that really most of the downdraft cooling process has come from two items, evaporation of rain and melting of hail and graupel. Nonetheless, we don't really see any evidence that this hail is mixed with much of any rain in that region. And we also don't really have any evidence of significantly melted hail either, since a large water torus seems to be absent. So I take us back to the arc disruption conceptual model and see if this is still valid, or did I gloss over something? In this case, I completely glossed over something. The KDP should likely be high or at least above 0.5. And even omission of KDP due to lower CC shouldn't automatically mean the hail is wet either. This is where you can use surrounding bins of, say, around 0 to negative KDP that can provide a sign that there's little liquid water mixed into the equation. So it is unlikely we have something like this image is depicting with tons of rain mixed with hail. Just doesn't seem to be happening. And so that might falsely make you believe we have a negative buoyancy problem. It's illustrated here by the old strong heat sink 2014 Markowski and Richardson conceptual model. That's not going on. And if we had more of a wet hail or rain mixed with hail, this probably would be valid. But since it's mostly dry hail with not a ton of liquid water, we don't seem to be getting this massive infusion of negative buoyancy. So instead, we have something that looks more like this. And I realize the video quality is not the best here, but note the complete absence of rain or signs of melting hail, along with really no signs of water splashing with the hail impacts. And I will add here that per conversations that the Stuart Goodland, Jeremy Martin had while he was out doing the storm survey with citizens living in that area, they indeed observed, I think they called it lime-sized hail with no rainfall existing. So we're getting confirmation that this was hailstones of whatever you want to call lime size, but dry hail. There was basically little to no liquid water content in that region. And so, this is where, despite the arc disruption, the lack of this significant infusion of liquid water here means that there wasn't likely much negative buoyancy injecting into that LFVE airstream. And so the Markowski and Richardson conceptual model, which they call their intermediate heat sink for tornadogenesis, is much more likely to be ongoing than the previous version. And so due to this critical step in using KDP to help differentiate dry hail regions from wet hail, the CWIP Supercell-based Tornadogenesis radar feature reference guide that I talked about earlier, but specifically the disruption portion shown on this slide, was updated to specifically address use of KDP and arc disruption analysis. And that's done to avoid doing what I did, incorrectly assuming an unfavorable setup for genesis. So in particular, as highlighted in the guide, we need to see the arc disruption with KDP values greater than 0.5 to truly be disruptive for genesis. So, however, when you have these regions of zero, around 0 to negative KDP, as noted here within the important notes, within an arc disruption, again, we have that included, dry hail is inferred, which means it's much less likely to be significantly adding negative buoyancy to the all-important LFVE airstream below the meso. So basically, if you're not meeting all of those key components, not just low ZDR, low CC, but also KDP is greater than 0.5, if you're not meeting all those criteria, then this null concept really cannot be applied because you're not meeting all those criteria. And so even though an arc disruption is something you should pay attention to, you need to be able, to the best of your ability, differentiate the wet versus dry hail scenarios. And that's shown with this Benkelman case. So that left me pondering, how common this really is. Maybe the Benkelman storm was a one-off event that simply doesn't occur very often, but it already kind of had an idea of several cases in my mind to go back and look at. And so this first case, a little further out, about 50, 55 nautical miles from the radar, starting at about T-3 minutes. And so we see hints of a region of raised ZDR, although maybe not a classic arc, but a ZDR shield that is abruptly disrupted by an area of negative to near 0 KDP values and reduced ZDR that is varying between slightly negative to slightly positive, although I don't have it shown here, but there was also reduced CC values. So similar to the Benkelman case, we likely have dry hail creating the disruption instead of wet hail mixed with rain. It's still favorable for genesis. This next case is a little closer to the RDA at about 25 to 30 nautical miles. We're going to start at T-7 minutes. So unlike the previous case, but closer to the Benkelman event, we start off actually with a non-disrupted ZDR and essentially minimal sign of hail. However, that changes quickly here by T-4. So kind of in that last few minutes that I got tripped up by with Benkelman, same thing kind of happens here with an obvious, what appears to be now disrupted ZDR caused by a region of around 0 ZDR and a large area of negative or missing KDP. Now, unlike the previous examples, this area of missing KDP due to very low CC is exceeding the amount of negative KDP. So, which does raise some questions, as to the extent of liquid water. But this is, as I mentioned earlier, this is where you use the adjacent bends to the best extent possible. And in this case, you immediately notice, most of the region contains either negative KDP or at best maybe KDP value slightly positive, but still largely less than 0.5. So we likely have a situation where existence of dry hail adds very little negative buoyancy. And so here's a case that might be a little fresher in your mind via the tornadic outbreak this past December 10th. Now in this instance, we'll use the same supercell that impacted the Mayfield, Kentucky area, the 2021 version of Mayfield, Kentucky, but investigate features several hours before that point, just because we're looking at, obviously, tornadogenesis, not once the storm was on cruise control. So we just start prior to the initial tornado developing over northeast Arkansas that kind of subsequently kicked off what we know now are hours of nearly continuous tornado tracks. So the storm is around 40 nautical miles from the RDA, and we're about 15, 20 minutes before genesis. So unlike the previous case, we're going to actually flip the order the disruption appears relative to a non-disrupted arc. So immediately we can see evidence, and there's some evidence right prior to this scan, but this is the best one where there was an arc along that forward flank reflectivity gradient, and a KDP foot a little deeper into the storm core with fairly resultant large separation vector angle. However, closer inspection, and this may trip up a few people, we do see, this small region near the rear flank forward flank interface that shows a disruption of the arc and contains KDP values close to 0 with some values being negative. Now, I will say, while not as clear-cut compared to the previous examples, given the lower Z values, this does indicate introduction of either some sparsely populated, likely sub-severe dry hailstones, or potentially even mixed with just a very low amount of extremely small drops. So either way, this means we don't have this, big massive infusion of wet hail and tons of liquid water that would obviously potentially disrupt not only the arc, but infuse this big area of negative buoyancy. So essentially, we have very little concern for this disruption leading to that. And ultimately, lest we not forget, this also tells us the diffuse circulation and velocity should intensify over the following 10 to 15 minutes, given the presence of the arc and a good separation vector. And again, it illustrates the prognostic nature of these tools instead of largely diagnostic, more reactive-based rotation. Now, fortunately, the next scan reveals the disruption fading, yet really, we have the same prognostic signal in the previous scan for increased risks of tornadogenesis the previous time as we do here when accounting for this dry versus wet hail issue. So last example here, just contrast these tornadic events dominated by dry hail to this non-tornadic case. And you get more of a rain mixed with wet melting hail scenario within the disruption. And the southern half of that light blue outline has a few missing bins, but KDP is generally greater than 0.5, along with ZDR just slightly positive, while the northern half of that disruption is seeing KDP values exceeding 4 to 5, along with ZDR values at best around 1. And so this is a solid indication of rain mixing with hail now injecting a substantial amount of negative buoyancy into that LFVE airstream. So to kind of sum all this up, it is important to reiterate that regardless of wet versus dry hail, a disrupted arc is not inferring that low-level size sorting and associated enhanced storm scale SRH is absent, as low-level mesointensification is typically still ongoing. And so this is where algorithms such as those displayed earlier will struggle, and so this is where we can beat the machines. But I can't reiterate this enough. Despite some of the amazing techniques and stuff we have with these algorithms, humans can still improve the decision making if they take the time to properly assess the storm and understand strengths and weaknesses. And so while it remains true that a disruption is providing some detail on the degree of negative buoyancy feeding that LFVE airstream that composes the tornado seed, existence of any hail does not always equate to strong negative buoyancy. And so, this is where, as a warning decision, you must differentiate dry or sparsely populated hail from environments where the hail is mixed with rain under wet, fast melting hail exists. And so unfortunately, ZDR and to a lesser degree CC may look very similar for wet versus dry hail, which again, I can attest to may lead to misinterpretation of what is ongoing. And so this is where the addition of KDP when assessing the arc disruption becomes important because, as I said a few moments ago, differentiating the wet versus dry hail regions is critical for correctly interpreting the probability of tornadogenesis. And so ran a little long here, but that's all I have. So I guess we can take any questions now from either one of our talks.